If you sit here with us for a second, just looking out the window of this Alaskan Bioforge field station, you can really feel how, I don't know, how incredibly vibrant the quiet actually is.
Yeah, it really is. It's not empty at all.
Right, exactly.
Yeah.
You've got this gentle breeze kind of pulling through the evergreens outside, and there's this pristine pond just, right beyond the glass.
You can actually hear the water sort of lapping against the edge if you listen closely.
Yeah, yeah, you can. And earlier there was a raven calling off in the distance. It's beautiful. But sitting right in front of us on this heavy wooden table is, well, it's the whole reason we're here. We have this massive stack of sources to go through with you today for this deep dive.
Oh, yeah. Decades of stuff. I mean, we've got field journals, biological surveys, USGS geological reports, climate data, you name it.
Right. And our mission is basically to take all these observations from this living laboratory around us and use them to understand a really fundamental scientific lens. It's called Cross-Cutting Concept 7. The topic is stability and change.
Which is really the perfect environment to anchor this kind of thinking. I mean, when you look out at those towering mountains behind the pond, your initial instinct is probably to see like a static postcard.
Totally. Just a pretty unchanging picture.
Exactly. But viewing the natural world through the lens of stability and change, it fundamentally alters how you understand, well, literally everything happening out there. In the forest, the water, the soil, right beneath us.
I have to admit, though, when I first looked at the syllabus for this concept, the word stability just felt completely lifeless to me.
Like boring.
Yeah,
Yeah.
like nothing is happening. It sounds like a rock just sitting on a desk. But I was trying to visualize what biological stability actually is. And I thought about the physical act of balancing.
Oh, that's a good way to look at it.
Right. Like if you stand up right now and try to balance on one foot to someone watching you from across the room, you might look perfectly still. You look stable.
But you're really not.
No. If you actually focus on what is happening inside your own body, your ankle and your foot muscles, they're constantly twitching. They're firing off these rapid microscopic adjustments, pulling left, pulling right, over and over again. And that's just to keep you from falling over.
And that physical tension, that's exactly what is happening in every single ecosystem on Earth.
Yeah.
Because scientifically speaking, stability is never just stillness.
Right.
True stability is a state of dynamic equilibrium.
Dynamic equilibrium.
It's a continuous balancing act.
Hmm.
And there's this mental framework we want you to use as we dig through these field reports today. Whenever you observe a natural system, just ask yourself 3 questions. What is stable? What is changing? And what evidence shows it?
Okay, so what is stable, what is changing, and the evidence?
Exactly. Because if you look at the numerical patterns, look for the slopes and the data we have here on the table, you'll start to see those invisible ankle muscles basically twitching everywhere.
So, if biological stability is just this illusion created by a million tiny adjustments, what exactly are the ecological muscles doing all the pulling and twitching?
Well, in science, we call those muscles feedback loops.
Yeah.
And specifically balancing loops or negative feedback.
Negative feedback, okay.
Right. These are the built-in systemic mechanisms that counteract any disruption.
Yeah.
So they're always trying to maintain homeostasis, which is really just a fancy word for biological balance.
Let's ground that in something we all experience. Like, if you step outside this field station right now in the dead of winter and you don't have a coat on, your body temperature is obviously going to drop.
Very quickly, yeah.
Right, so that is a sudden disruption to your internal system. Instantly, these thermoreceptors, which are basically specialized nerve endings in your skin, they detect that drop.
Right, the sensor goes off.
Exactly, and they send this rapid fire signal straight to the hypothalamus in your brain. And your brain responds by triggering your skeletal muscles to rapidly contract and relax. Basically, you shiver.
You shiver, yeah.
And the physical friction of that shivering generates heat, which raises your core temperature back to normal. The disruption is totally counteracted.
And the cool part is, once your core temperature normalizes, the brain just stops sending the signal.
Oh, right. The shivering just ceases.
Exactly. The output of the system, which is the heat, it loops back around to turn off the original input. That's a balancing loop on a microscopic scale. But the fascinating thing in these biological surveys we're looking at is seeing that exact same mechanism play out on a massive regional scale.
Like with animals.
Yeah, look at the data here, tracking the Canadian lynx and the snowshoe hare.
Okay, let me grab that folder. I'm looking at that data right now, and I'm honestly a little bit confused. How do a predator and its prey keep an ecosystem stable? Because the lynx hunting and killing a hare, That doesn't sound very stabilizing.
Not for the hair, anyway.
Right, especially not for the hair.
Well, you have to zoom out, right? Look at the population data over, say, a 10 or 20-year period. It's a continuous, deeply connected dance. So let's say the hare population surges because of a particularly mild winter.
So there's lots of plant growth, lots of food for the hares.
Exactly. Suddenly, there is a massive buffet of food for the lynx. So the lynx are well fed, their reproductive success goes way up, and their population increases.
Okay, that makes sense.
But as the lynx numbers swell, obviously they hunt more hares, and eventually that predation pressure becomes so heavy that the hare population begins to just plummet.
Oh, wow. So they eat themselves out of house and home, basically.
Essentially, yeah. With fewer hares to eat, the swollen lynx population faces starvation, and then their numbers drop sharply.
And then I'm guessing the relief from all those predators dying off allows the surviving hares to recover and multiply again.
You got it. It's a cycle.
So there's a lag time. The hare population spikes, and the lynx population spikes right behind it, which pushes the hares down, which pushes the lynx down. They are literally the opposing muscles in the ankle, twitching back and forth across the decades to keep the overall ecosystem upright.
The primary takeaway for you here is that whenever you see a beautifully balanced natural system, you're not looking at a static painting. You are looking at a hidden loom of opposing forces just constantly pushing back against each other to maintain that dynamic equilibrium.
Which, makes me wonder about the limits of that system. I mean, if stability is just this exhausting, never-ending balancing act, what happens when the ecosystem gets pushed too hard?
That's the big question.
I'm kind of thinking of a game of Jenga. Like, you can carefully pull out one wooden block, then another and another. And to anyone watching, the tower still looks totally healthy. It's standing perfectly upright. It looks stable.
Until it isn't.
Right. There is always that one final block. You pull it, you cross the tipping point, and the entire structure just collapses into a completely new, messy state on the table. It doesn't, wobble back to normal. It fundamentally transforms.
And we're seeing that exact Jenga collapse documented right here in these forestry reports from South Central Alaska. Entire landscapes are undergoing what ecologists call a regime shift.
A regime shift.
Yeah. And the disturbance is being driven by an insect the size of a grain of rice, the spruce bark beetle.
But wait, the spruce bark beetle is native to this area, right? It's lived in these white and lut spruce forests for thousands of years without completely destroying them. Why is a native beetle suddenly causing millions of acres of mature forest to die off?
The climate data actually holds the answer to that. Historically, Alaska's bitterly cold winters acted as a massive balancing loop. Because of the freezing temperatures, a spruce beetle's metabolic rate was forced to slow down, meaning it took them 2 full years to mature and complete their reproductive cycle.
Oh, okay, so the cold kept their population perfectly in check.
Exactly. But the temperature records show an average winter increase of about 1.5 degrees Celsius in this region.
Which doesn't sound like a lot.
Right, it's a minor shift to us. But for the beetle, it completely changes their internal chemistry. They produce enough antifreeze proteins to survive the milder winter, allowing them to mature and fly in just 1 year.
Wow, so they've effectively doubled their reproductive rate.
Doubled it, yeah.
Okay, I understand the beetles are multiplying faster, but I still don't get why the trees are completely defenseless. I mean, a spruce tree that has been evolving for thousands of years must have some kind of armor against a tiny beetle.
Oh, they absolutely do. Healthy spruce trees rely on something called turgor pressure. They basically use the water pressure inside their vascular system to manufacture and secrete this thick, toxic, sticky sap called oleoresin.
Oleoresin.
Right. When a beetle tries to bore into the bark, the tree uses that intense internal pressure to literally pitch the beetle out, just suffocating it in a tomb of sap.
Okay, so turgor pressure is sort of like the water pressure inside a garden hose.
Correct.
If the water is turned up high, the hose is completely rigid and strong.
Good analogy, yeah.
But these climate reports show that this region has been experiencing prolonged, multi-year droughts. So the soil is super dry. The roots can't pull up enough moisture. So the garden hose just loses its pressure and goes totally limp.
Exactly. The trees simply do not have the physical water required to manufacture that defensive sap.
So that's a massive block being pulled from the Jenga tower.
A huge one. And once that turgor pressure drops and the defense is broken, a reinforcing loop takes over.
A reinforcing loop.
Yeah, this is positive feedback. It's the kind that destabilizes the system. When a few pioneer female beetles successfully bore into a drought-stressed tree, they release aggregation pheromones.
Oh, no. Like a beacon.
Exactly like a beacon. They're powerful chemical signals that reach thousands of other beetles in the area. It triggers a mass attack. They swarm the trunk, bore beneath the bark, and immediately attack the phloem.
Okay, wait. The phloem is basically the tree's circulatory system, right? Like
Right.
the roots use xylem to pull water up, but the leaves in the canopy use the phloem to push the sugars they make during photosynthesis down to feed the rest of the tree.
Correct. And the beetles mine right through that phloem layer to lay their eggs. They completely sever the connection between the canopy and the roots. They essentially girdle the tree from the inside out, starving it to death.
Wow. So you look out the window at millions of acres of vibrant green spruce canopy, and within a few short seasons, you hit that tipping point. The canopy turns this rusty, bleeding red as the needles die, and then it just fades to a skeletal, lifeless gray.
It's tragic. But the cascading effects, they don't just stop with the dead trees.
Really?
Ecosystems are so deeply interconnected. When the mature canopy dies and drops its needles, sunlight suddenly floods the forest floor. And that's a place that has been cool and heavily shaded for centuries.
Right. So everything down there is used to the dark.
Yeah, and this triggers a massive secondary change. The biological surveys show that a fast-growing native plant called Canada blue joint grass exploits that new sunlight.
Hmm?
The data shows its coverage rocketing from less than 1% to nearly 50% of the entire forest floor.
Wait, I'm reading here in this folder that Canada blue joint grass grows incredibly fast in the spring, but then it completely dries out and dies back every summer, leaving behind this thick, dense mat of highly flammable kindling.
Yeah.
So the Jenga tower hasn't just fallen. The pieces have literally caught fire. We've gone from a stable, shady, cool, fire-resistant spruce forest to a skeletal canopy sitting on a bed of dry fuel. The system has crossed a permanent tipping point. It shifted into a fire-prone grassland.
And this whole phenomenon forces us to question our own perception of change. When a massive forest turns gray or a Jenga tower falls, human beings tend to perceive it as a sudden, violent event. But sudden changes are almost always a result of gradual, completely invisible changes accumulating over a long period of time.
It's kind of like putting a plastic container of liquid water into a freezer. Well, if you watch it, the temperature drops gradually, right? 5 degrees Celsius to 4 to 3 to 1. Over all that time, it looks exactly the same to the naked eye. It's just liquid water. The change is invisible. But the exact second the internal temperature hits 0 degrees Celsius, it crosses the physical threshold and suddenly, rapidly snaps into solid ice.
The sudden snap was just the culmination of a long, gradual chill.
Exactly.
We're actually seeing a breathtaking example of that exact freezer effect deep in the Brooks Range of Alaska. The geological reports we have here, they document dozens of pristine, crystal-clear wilderness rivers that have suddenly turned bright opaque orange.
Opaque orange.
Yeah, they literally look like they're full of rusting iron.
Wow. Well, an opaque orange river is definitely not a stable state. What is the invisible, gradual change that caused the sudden snap in the water chemistry?
The gradual change is the thawing of the permafrost, the permanently frozen ground that makes up much of the Arctic tundra. For decades, subtle atmospheric warming has been slowly penetrating the deep soil.
So that's the invisible temperature drop in the freezer analogy.
Exactly. And as the permafrost finally thaws and the soil physically slumps, the deep groundwater gets rerouted. It begins to flow through newly unfrozen layers of bedrock and soil that contain sulfide minerals, specifically pyrite.
Pyrite, like fool's gold.
Yes, fool's gold.
So the groundwater hits the pyrite that has been locked in ice for thousands of years. What is the actual chemical mechanism turning the water orange, though?
Well, when oxygen, water, and pyrite interact, it triggers a microscopic chemical weathering process called acid rock drainage. The reaction produces sulfuric acid and dissolved iron.
Oh, acid. That can't be good.
No. The sulfuric acid drastically lowers the pH of the groundwater, making it highly acidic. And this acidic water then acts like a chemical sponge, leaching toxic trace metals, copper, zinc, cadmium, out of the surrounding rock.
And when that highly acidic, metal-heavy groundwater eventually bubbles up into the streams and hits the open air, the dissolved iron oxidizes.
It literally rusts.
It rusts in the water, turning the river that brilliant, terrifying orange. And I assume the sudden spike in acidity and the heavy metals coat the gills of local fish.
Yeah, it completely wipes out populations of dolly varden trout. It is an entire aquatic food web collapsing, all because of a slow, invisible thaw deep underground.
That is wild. But I'm looking at these field reports, and the thawing permafrost makes sense for the Orange Rivers, but then there's this entire thick section in the folder on, wait, beavers.
Beavers, yeah.
I am struggling to connect the dots here. How does a beaver moving north into the tundra cause the ground to melt?
Well, historically, beavers are forest animals. They need wood. But as the climate has gradually warmed, woody shrubs like willow and alder have expanded northward into the treeless Arctic tundra.
Okay.
The beavers simply followed their food source, and they brought their profound engineering skills with them.
Right, they build dams. But why is a beaver dam so dangerous in a tundra environment?
It fundamentally alters the hydrology and the thermal mass of the landscape. By damming narrow streams, beavers create deep, sprawling ponds. And deep water doesn't freeze all the way to the bottom in the winter, and water is excellent at holding on to solar heat during the summer.
Oh, I see.
So these new, deep ponds act as massive thermal reservoirs sitting directly on top of the frozen ground. They hold the heat and aggressively melt the surrounding permafrost.
And as the permafrost melts and collapses into the pond, I imagine it drags tons of dead organic matter like grasses, roots, soil down with it into the digged water.
Yes, and at the bottom of a deep, stagnant pond, there is very little oxygen. It creates an anaerobic zone.
Yeah.
Down there, specialized microbes called methanogenic archaea start breaking down all that newly thawed organic matter.
Okay, so they're digesting it.
Yeah, but because they are digesting the carbon without oxygen, their biological byproduct isn't carbon dioxide, it's methane.
Oh, wow. And methane is a greenhouse gas that is, what, roughly 25 times more potent at trapping heat than carbon dioxide.
Yep.
That is a wild, dizzying feedback loop. The gradual warming brings the shrubs bring the beavers build the ponds melt the permafrost releases methane, and the methane causes more gradual warming.
It's biology altering geology, which alters the climate.
It really is. I mean, I have to push back a little here. Sitting in this field station, going through folder after folder of rusting rivers and dying forests, it feels incredibly apocalyptic. Like, is change just a synonym for destruction in these systems?
I know, it is so easy to fall into that trap. But we have to reframe how we view ecological change. In science, change is not inherently bad. It is a mechanism of life. And this brings us to the core concepts of resilience and succession.
Resilience.
Right. Ecosystems possess built-in buffers. Resilience isn't about being perfectly rigid, trying to resist every force of nature. It's about a system's capacity to absorb a shock, bend under the pressure, and eventually recover its core functions.
Kind of like jumping on a trampoline. Like the mat stretches deep under your weight, absorbing the sudden disturbance, but when you step off, the tension in the springs snacks it back into shape.
That's a great way to picture it.
But what does an ecological trampoline actually look like?
We can look at the Pacific salmon populations right outside this station for a perfect example.
Right.
We know that salmon are highly stressed by warming river temperatures. The physical mechanism there is gas solubility. As water gets warmer, its ability to hold dissolved oxygen decreases.
So the fish literally suffocate in warm water.
Exactly. But the landscape offers a buffer. While many rain-fed rivers in Alaska are becoming dangerously warm and oxygen depleted during summer heat waves, we also have streams that are fed entirely by high-altitude melting glaciers.
Oh, and those glacial streams act as thermal buffers. The water coming off the ice is obviously freezing cold and highly oxygenated.
Right. During a brutal heat wave, these glacial streams provide critical, life-saving refuges. The migrating salmon navigate into these cold pockets to rest and breathe. The ecosystem bends under the pressure of the heat waves, but the glacial buffer prevents the population from completely collapsing.
That's amazing. But what about when a system does seemingly collapse, like that mature spruce forest burning to the ground after a beetle outbreak? That feels like the end of the story.
But it's not at all. That is just the beginning of ecological succession. A devastating disturbance like a wildfire is actually part of a larger, deeply necessary cycle. You see, in a cold, mature forest, dead organic matter accumulates on the forest floor, but it decays incredibly slowly. Essential nutrients become permanently locked up in the wood and needles.
So a fire acts as a rapid oxidizer.
Exactly.
It burns through the cellulose and lignin, destroying the dead matter and instantly returning all those locked up minerals and nutrients back to the soil in the form of rich ash. It hits the reset button.
It does. And with the dense, dark spruce canopy gone, the forest floor is flooded with sunlight again. This allows completely different species to colonize the scorched earth.
Hmm.
Sun-loving pioneer species like the bright purple fireweed just explode across the landscape.
And then they are followed by fast-growing deciduous trees, right? Like birch, willow, and aspen.
Yeah, which fundamentally changes the food web. A moose, for example, cannot survive in a dense, mature spruce forest. Spruce needles are full of bitter tannins and offer terrible nutrition, and the canopy blocks the shrubs a moose needs to eat.
But a moose absolutely thrives on young willow and birch saplings.
Right.
So the destructive fire actually creates a new, temporary, stable state that supports a completely different community of life. And then eventually, over decades or centuries, the slow-growing spruce might return, shading out the birch and returning the system to its original state. The change itself is the engine of renewal.
Exactly. So as we close these field journals and sort of wrap up our time here at the Bioforge today, I want you to take one last look out that window at the pond, the deep forest, and the mountains.
It looks different now, doesn't it?
It really does. Think back to the thinking routine we started with. What is stable? What is changing? What evidence shows it? If you look closely at the evidence, you will understand that stability is not stillness. It is balance over time.
Balance over time.
It's the links and the hair pulling back and forth. It's the ankle muscle constantly twitching to keep you upright. It is the capacity to bend with the heat, to burn, and to regrow.
You know, watching all these twitching ecosystems adapt to disruption, it really makes you look at our own human infrastructure a bit differently. We've seen how perfectly rigid, unmoving systems in nature, like a tree that can't produce sap in a drought or frozen ground that can't handle a beaver pond, they eventually cross a tipping point and shatter.
Yeah, rigidity is dangerous.
It makes you wonder about the cities, the bridges, and the societies we build. Like, do we design our world to be perfectly rigid, trying to stubbornly resist every force of nature? Or, should we be designing our infrastructure to twitch, to bend, and to dynamically adapt, just like the living systems right outside this window?
That's a profound question to leave on.
Thank you for joining us at the Bioforge for this deep dive. Keep looking for those invisible changes, and we will catch you next time.